Hello students, today we are going to discuss NCERT section 9.7.2 of chapter Ray Optics and Optical Instruments. This is the disclaimer. So welcome to our session on Ray Optics and Optical Instruments. Today we will focus on understanding the fundamental principles and components of telescopes. We will explore both refracting and reflecting type telescopes, which are essential tools in astronomy. Let's dive into our first objective, understanding the basic principles, components, and working of telescopes. We will cover how refracting telescopes use lenses to gather and focus light, while reflecting telescopes use mirrors. Pay attention to the differences in design and application, as these are crucial for their respective uses in observing celestial objects. Now let's move on to the calculating the magnifying power of telescopes. We will analyze performance characteristics and discuss various modern telescopes and their applications. This will help you appreciate the advancement in telescope technology and their impact on scientific discoveries. Remember, the magnifying power is a key factor in determining how much detail we can see in distant objects. So the index provides a roadmap of topics covered in the presentation. In this case, it specifically mentions the NCERT section 9.7.2 on telescopes. Now we will discuss the purpose and principle of telescopes. Here we see an image of a refracting type telescope. This type of telescope uses lenses to bend light and form an image. It's important to note that refracting telescopes are one of the earliest type of telescopes used in astronomy. They are known for their ability to provide clear and sharp images of distant celestial objects. Telescopes are designed to provide angular magnification of distant objects. This means they make faraway objects appear larger and closer, allowing us to study them in greater detail. They do not magnify the smaller objects. They bring the distant objects closer to our eye. They observe already large bodies, heavenly bodies, but they are at a very far distance from us. Okay, so what telescope do? It brings the object closer to our eyes. Okay, what microscope do? It magnify the very small object. Okay, so the magnification is essential for astronomers who need to observe planets, stars, and galaxies that are light years away. The key function of a telescope is to collect light from distant sources and form magnified images. This is achieved through the telescope's lenses or mirrors, which gather and focus light to create a detailed image. The more light a telescope can collect, the better the quality of the image it can produce. A telescope consists of two main components, the objective and the eyepiece. The objective is the primary lens or mirror that gathers light, while the eyepiece magnifies the image formed by the objective. Understanding these components helps us appreciate how telescopes work to bring distant objects into view. Two critical performance parameters of telescopes are light gathering power and resolution. Light gathering power refers to the telescope's ability to collect light, which is crucial for observing faint objects. Resolution, on the other hand, determines the telescope's ability to distinguish between two closely spaced objects. Both factors are vital for producing clear and detailed images. Here we have an image of a refracting telescope labeled figure 9.25. Notice the long tube and the lenses at both ends. This setup is essential for gathering and focusing light from distant objects. The image helps us visualize the basic structure of a refracting telescope. So refracting telescopes use lenses for both the objective and the eyepiece. This is important because lenses are responsible for bending light to form the images. The objective lens gathers light while the eyepiece lens magnifies the image for viewing. So you can see the parallel rays of light are coming from a distant object, and after refracting through the objective lens, image is formed at a focal plane of objective lens. Okay, plane perpendicular to the principal axis passing through focus, that is focal plane of objective lens. So image is formed at focal plane of objective lens. Okay, then that image will act as an object for the eyepiece, and that eyepiece will form the magnified image of this object. Okay, the objective lens has a large focal length and aperture. Why objective has large focal length and eyepiece have small focal length, we will discuss it. This means it can gather more light. Okay, for gathering more light, which is crucial for observing faint distant objects. The objective forms a real inverted image at its focal plane, which is then magnified by the eyepiece. The eyepiece has a short focal length and acts as a simple microscope. Its job is to magnify the images formed by the objective lens, allowing us to see details that are not visible to the naked eye. This is why the eyepiece is crucial for the telescope's function. Finally, the image produced by a refracting telescope is inverted. This is a common characteristic of a telescopic images, but it doesn't affect the observation of celestial objects. Understanding this helps us interpret what we see through the telescope. Now let's delve into the concept of magnifying power. The magnifying power, denoted as M, is the ratio of angle beta, which the final angle subtends at the eye, to the angle alpha, which the objects subtends at the lens or the eye. Okay, as you can see in the diagram also, the alpha angle is the angle subtended by object at the eye, or we can say objective lens, and beta is the angle subtended by the final image at the eye. Okay, the ratio is fundamental in determining how much larger the image appears compared to the actual object. The formula for magnifying power is given as M equals to beta by alpha. Tan beta here is equal to H upon Fe. You can see in the diagram, tan theta is equal to perpendicular upon base. So tan beta here is H upon Fe. Okay, and tan alpha here is H upon F naught. Since angle beta and alpha are small angles, we use the approximation here that tan theta approximately equal to theta for small angle theta. Now put the value of beta and alpha in the expression and magnifying power M finally came out to be F naught by Fe. Okay, mark it as 9.46 equation. Here F naught is the focal length of the objective lens and Fe is the focal length of the eyepiece. Understanding this formula is key to calculating how much telescope can magnify an image. Remember, the larger the ratio, the greater the magnification. Now let's discuss the length of the telescope tube. For normal adjustments where the final image is formed at infinity, the length of the telescope tube, denoted as L, is crucial. This setup ensures that the telescope is optimized for viewing distant objects. The formula for the length of the telescope tube is L equals to F naught plus Fe. Here F naught is the focal length of the objective lens and Fe is the focal length of the eyepiece. Understanding this formula is key to calculating the necessary tube length for the clear images. In addition to astronomical observations, terrestrial telescopes include a pair of inverting lenses. These lenses ensure that the final image is erect, which is important for viewing objects on Earth without them appearing upside down. Refracting telescopes are versatile and can be used for both terrestrial and astronomical observations. This dual functionality makes them valuable tools for a wide range of applications, from staring into space to bird watching. Let's consider the specifications of a telescope. We have a telescope with two key focal lengths, the objective lens and objective lens focal length denoted as f0 and eyepiece focal length denoted as fe. These values are essential for calculating the telescope's magnifying power. The objective lens has a focal length of f0 equals to 100 cm. This lens is responsible for gathering light and forming an initial image. The longer the focal length, the more light it can collect, which is crucial for observing distant objects. The eyepiece has a focal length of fe equals to 1 cm. This lens magnifies the image formed by the objective lens. A shorter focal length in the eyepiece results in greater magnification, which is what we aim for in telescope. Now let's calculate the magnifying power of the telescope. The formula is m equals to f0 by fe equals to 100 by 1 equals to 100. This means the telescope can make objects appear 100 times larger than they are to the naked eye. Understanding this calculation helps us appreciate the power of telescopes in astronomy. Now magnifying power of this telescope is 100. This means that a telescope can make objects appear 100 times larger than they do to the naked eye. Magnifying power is a critical feature of the telescope as it determines how much detail we can see in the distant objects. Imagine observing a pair of stars that are separated by 1 arc minute. With the telescope's magnifying power of 100, these stars would appear separated by 100 arc minutes. This is a significant increase in apparent separation, allowing us to resolve details that are not visible to the naked eye. 60 arc minutes are equal to 1 degree. Therefore, 100 arc minutes is equivalent to 1.67 degrees. This calculation shows how the telescope enhances our ability to distinguish between closely spaced objects in the sky. Understanding these calculations helps us appreciate the precision and capability of telescopes in astronomical observation. Okay, so actually these stars, when we view them with the naked eye, are separated by 1 arc minute. But when we see them using telescope whose magnifying power is 100, so they appears to be separated by 1.67 degree, means 100 times the 1 arc minute. Okay, so that is actually the function of the telescope, that it can resolve two distant objects into a separate entities. Okay, so it says design concentration. Okay, it's performance characteristic. So there are mainly two performance parameters of astronomical telescope, that are light gathering power and involving or resolving power or resolution. The first concept to grasp in the light gathering power of a telescope, this is essentially how much the light the telescope can collect, which is vital for observing faint objects in the sky. The more light a telescope can gather, the better it can reveal distant stars and galaxies. Mathematically, the light gathering power is proportional to the square of the diameter of the telescope's objective lens or mirror. This means that even a small increase in diameter can significantly enhance the telescope's ability to gather the light. Here D represents the diameter of the objective. It's important to note that a larger diameter allows the telescope to capture more light, making it possible to see fainter objects that would otherwise be invisible. With larger diameters, telescopes can observe fainter objects, which is crucial for astronomers who want to study distant galaxies and stars. This is why many modern telescopes are built with the larger objectives to maximize their light gathering capability. Let's delve into what resolving power means. It's the telescope's ability to differentiate between two closely spaced objects in its field of view. This is essential for astronomers who need to see fine details in celestial bodies. Think of it as the telescope's sharpness in viewing the distant stars. Okay, so how much fine details a telescope can show? Like it can show two stars that are separated by 1 arc minute when viewed by naked eye. When viewed by the telescope, they appears to be separated by 1.67 degree, which is 100 times 1 arc minute. So what is the telescope's ability to show two different objects separately? Okay, to resolve them or to show the fine details. Here is the formula for resolving power. Resolving power equals the diameter of the objective divided by 1.22 times the wavelength of light. This formula shows how resolving power is mathematically determined. Note that D represents the diameter of the telescope's objective lens or mirror, and lambda is the wavelength of light being observed. The resolving power is significantly influenced by the diameter of the objective. A larger diameter allows the telescope to capture more light, enhancing its ability to resolve finer details. This is why telescopes with larger objectives are preferred for detailed astronomical observations. To maximize resolving power, optical telescopes are designed with large diameter objectives. This design choice is crucial for achieving high resolution images of distant objects. As we wrap up this session, remember that the larger the objective, the better the telescope's resolving power. Let's see the advantages of large objective of telescope. So let's start with the first advantage. Large objective allows us to observe fainter objects. This means telescopes with a bigger lenses can capture more light, making it possible to see distant stars and galaxies that are not visible to the naked eye. The second advantage is better resolution. This is important because it allows us to distinguish between objects that are close together in the sky. Think of it having a high definition TV versus a standard one. The details are much clearer in the high definition TV. Okay, similarly, the telescope with better resolution will show the finer details in the sky, in the space. The third advantage is that large objectives provide brighter images. This makes it easier for astronomers to study celestial objects in details, as the images are more vivid and easier to analyze. Finally, let's look at an interesting fact. The largest lens objective in use today has diameter of 40 inches or about 1.02 meters and is located at the Yerkes Observatory in Wisconsin, USA. This highlights the scale and capabilities of modern telescopes. Okay, so this is the refracting type telescope, the largest refracting type telescope. There are some limitations of refracting type telescopes. First, let's talk about chromatic aberration. This occurs when different colors of light focus at different points, leading to a blurred image. It's a significant issue in refracting telescopes that affect image clarity. Chromatic aberrations can be partially corrected using optical lens systems known as achromatic doublets. These systems are designed to minimize the color distortion by combining two lenses, helping to improve the image quality. Now let's move on to the mechanical limitations. Large lenses in refracting telescopes are very heavy, which poses significant challenges in terms of handling and support. Okay, so what are the mechanical limitations? So supporting large lenses, especially those over 1 meter in diameter, is problematic because they are only supported at the edges. This can lead to structural issues and limits the size of the lenses that can be effectively used. Okay, so manufacturing large, high quality lenses is also very expensive. So large lenses are very, very heavy. So they are difficult to handle or difficult to hold within the telescope because they are supported only on the edges. So also manufacturing large quality lenses is also very expensive. Okay. So support problem for lenses of 1 meter since lenses are only supported at the edges. Also manufacturing of the lenses is expensive for large high quality lenses. Okay, so in conclusion, refracting telescopes have significant limitations that affect their performance and practicality. Understanding these challenges help us appreciate the advancements in telescope designs and shift towards alternative solutions. Here we have an image of a reflecting type telescope. Reflecting telescopes use mirrors to gather and focus light, which is a key difference from refracting telescopes that use lenses. Notice the design and structure which allows for capturing clearer images of celestial bodies. So this telescope, this is the image of James Webb Space Telescope, okay, which is sent by NASA to observe the galaxies and planets or stars. So one challenge with using lenses in telescopes is the difficulty and expense involved in making large lenses that are free from chromatic aberration and distortion. Chromatic aberration occurs when different colors of light are focused at different points, leading to blurry images. This is why alternative like mirrors are often preferred. Modern telescopes have shifted towards using concave mirrors instead of lenses for the objective. Concave mirrors can focus light without the chromatic aberration issues associated with the lenses, providing clearer and more accurate images of the distant objects. Okay, so there are no chromatic aberrations. All the colors focus on one point after reflecting from the mirrors. Okay, so in the case of mirrors, chromatic aberrations can be eliminated. Telescopes that use mirror objectives are known as reflecting telescopes. This design is crucial for astronomers as it allows for larger aperture and better image quality, making it easier to study distant galaxies and stars. Reflecting telescopes have become the standard in modern astronomy. Let's delve into the advantages of reflecting telescopes over refracting ones. Reflecting telescopes do not suffer from chromatic aberrations because mirrors reflect all colors equally. This means clearer and more accurate images, which is essential for astronomical observations. Another advantage is the lighter weight of reflecting telescopes. Okay, so for same diameter, lens will be heavier than mirror. Okay, so mirrors can be supported from behind also. Lenses cannot be supported from behind. They can only be supported at edges because light should pass through the lens, na? But mirror will reflect the light. So they can be supported from the behind, making the structure more stable and less difficult to handle as compared to lenses. which need to be supported around the edges. This design allows for easier handling and construction of the larger telescopes. Reflecting telescopes can have larger apertures, which means they can collect more light and provide better resolution. The largest current reflecting telescopes have apertures up to 10 meters in diameter, allowing astronomers to see fainter and more distant objects in universe. Okay, so largest refracting telescope have lengths of diameter around 40 inches, that is 1 meter around. Okay, but largest current reflecting telescope have diameter 10 meters of the objective mirror. Okay. Finally, reflecting telescopes are less expensive to build when it comes to large apertures. The cost effectiveness is due to the simpler designs and materials required for mirror compared to lenses, making them a preferred choice for large-scale astronomical research. We have covered the key advantages of reflecting telescopes, including no chromatic aberration, lighter weight, large aperture, and cost effectiveness. These features make them. Here we have a schematic diagram of the Cassegrain telescope. Notice the primary mirror, which is a large concave parabolic mirror. This mirror is crucial because it gathers light and reflects it towards the secondary mirror. Pay attention to how the light path is designed to maximize the telescope's efficiency. Okay, so mirror used here is not perfectly concave, it is parabolic. Okay, why parabolic mirror is used? To eliminate the chromatic aberrations. Inability of a mirror to focus light on one point. So to eliminate that aberration, we used parabolic mirrors. Okay, or inability of mirror to focus all the light rays, marginal or paraxial, to one point. To eliminate that inability, to eliminate that aberrations, we used parabolic mirrors instead of perfectly concave mirror. Okay, so this mirror is crucial because it gathers light and reflects it towards the secondary mirror. The secondary mirror in a Cassegrain telescope is a small convex hyperbolic mirror. This mirror plays a key role in redirecting the light back through the primary mirror. The shape of the secondary mirror is specifically chosen to help focus the light more effectively, contributing to the telescope's compact design. One of the main advantages of the Cassegrain telescope is its long effective focal length despite its compact size. Okay, this means it can provide high magnification without being physically large, making it easier to handle and use. This design is particularly beneficial for amateur astronomers and observatories with limited space. Okay, so large focal length means large focal length of the objective mirror. Let's look at the light path within the telescope. After the light rays reflect off the primary mirror, they hit the secondary mirror. The secondary mirror then reflects the light back through the hole in the primary mirror. This clever design allows the telescope to be shorter while still providing a long focal length. Finally, after passing through the hole in the primary mirror, the light rays reach the eyepiece. The eyepiece is where the final image is viewed. This setup allows for a clear and magnified view of distant celestial objects, making the Cassegrain telescope a powerful tool for stargazing. We have covered the key components and advantages of Cassegrain telescope. Remember, the primary and secondary mirrors work together to provide a compact yet powerful optical system. So first up is there are some famous telescopes. So first is Yerkes Observatory, which houses the largest refracting telescope with a 40-inch length. This telescope has been pivotal in astronomical research, allowing scientists to observe celestial bodies with great clarity. Next, we have the Keck telescopes in Hawaii. These are twin 10-meter reflecting telescopes that have significantly advanced our ability to study distant galaxies and stars due to their large size and advanced technologies. The Mount Palomar Observatory in California features 200-inch reflecting telescope. This telescope was once the largest in the world and has been instrumental in the many astronomical discoveries, including the study of galaxies, structure of galaxies. Now let's shift our focus to Indian astronomy. India has made significant contributions with its own observatories and telescopes, which we will explore next. The Kavalur Observatory in Tamil Nadu is home to a 2.34-meter reflecting telescope. This facility has been crucial for various astronomical studies, including the observation of comets and asteroids. Modern advancements have led to the development of automated telescopes. These are computer-controlled systems that allow for precise and efficient observation, enhancing our ability to monitor celestial events. Space telescopes offer a unique advantage as they observe above the Earth's atmosphere, eliminating atmospheric distortion. Let's delve into some of most notable space telescopes. So the Hubble Space Telescope is a prime example of the space telescope that operates above atmospheric disturbances, provide clear and detailed images of the universe. The James Webb Space Telescope, set to succeed Hubble, focuses on infrared observations. This capability allows it to peer through cosmic dust and study the formation of stars and galaxies. Space telescopes have several advantages, including the absence of atmospheric interference and the ability to access ultraviolet and infrared wavelengths. These features enable astronomers to gather data that ground-based telescopes cannot. So let's see summary. Telescope is an optical device that bring distant objects closer to our eye. Let's dive into type of telescopes. There are two main types of telescopes: refracting telescopes, which use lenses, and reflecting telescopes, which use mirrors. Understanding the difference between these two is crucial as it affects how they gather and focus light. Now let's talk about magnifying power. This is the ratio of focal length of the objective lens to the focal length of the eyepiece, represented as f0 by fe. This formula helps us understand how much larger an object appears when viewed through the telescope. Next, we have the concept of telescope length in normal adjustments, which is simply the sum of focal lengths of the objective and the eyepiece. L equals to f0 plus fe. This is important for setting up the telescope correctly to get a clear image. Light gathering power is another critical aspect. It depends on the area of objective lens, which is proportional to the square of its diameter, proportional to d square. A larger diameter means more light can be collected, resulting in a brighter image. Finally, let's discuss resolving power, which is given by d by 1.22 lambda, where lambda is the wavelength of light and d is the diameter of the objective. This tells us how well the telescope can distinguish between two close objects, which is essential for detailed and finer observations. Refracting telescopes have limitations like inability to focus on all colors of light at one point, and they are difficult to handle and manufacture. Now let's explore the advantages of reflecting telescopes. Unlike refracting telescopes do not suffer from chromatic aberration because they use mirrors instead of lenses. This design also allows them to be lighter and to have larger apertures, which means they can collect more light and provide better images of the distant objects. We will look at Cassegrain design, a popular type of reflecting telescope. This design uses a parabolic primary mirror and hyperbolic secondary mirror. The parabolic mirror helps focus light to a point, while the hyperbolic mirror reflects the light back through a hole in the primary mirror, allowing for a more compact telescope design. The Yerkes Observatory houses the largest refracting telescope ever built, showcasing the pinnacle of refractor design. In contrast, the Keck Observatory features modern reflecting telescopes, which are among the largest in the world and utilize advanced technologies to observe the universe. Finally, we will touch on specialized types of telescopes: radio telescopes, which detect radio waves from space, and space telescopes like the Hubble and the James Webb, which operate outside Earth's atmosphere, provide unique insights into the cosmos. These instruments allow astronomers to study celestial phenomena that are otherwise invisible to optical telescopes. There are some practice questions. In first question, write the formula for magnifying power of a telescope. Now let's reveal the next question. In a refracting telescope, both the objective and eyepiece are lenses. Specifically, they are convex lenses. This is important because convex lens converge light, which is essential for forming clear images in telescopes. Moving on to the next question, we have the formula for length of a telescope in normal adjustment. This is the sum of focal length of objective and the eyepiece. Understanding this helps us design telescopes that are both effective and practical in size. Next, let's discuss limitations of refracting telescopes. Okay, so name one major limitation of refracting telescope that reflecting telescope don't have. So which component of a telescope is primarily responsible for its light gathering power? Okay, so let's consider what gives a telescope its light gathering power. The primary component responsible for this is objective lens or mirror. Okay, so these are some practice questions. So this is all about today's lecture. I hope you enjoyed the session. Thank you.